Good afternoon to the examiner and supervisor. My name is Rafella Evdia, and today I will presenting my final year project titled an optimization model for procurement cost minimization, a case study of a Sarawak Lapis bakery. This project falls under the domain of computational science, specifically focusing on operation research applied to local small and medium enterprise (SME). Let's begin with the context of the study. Sarawak is famous for its cake lapis industry. While these cakes are cultural icon, the business side is challenging. Most of these bakeries operate as SME. They face a unique operational challenge. Their procurement is fragmented. They don't just buy from one place. They source ingredient from wholesaler, hypermarket, and increasingly online platforms like Shopee. Currently, most bakery owners make decisions based on intuition or convenience. They might drive to the nearest supermarket or buy from a supplier they've known for years. However, this creates a risk. By ignoring the complex trade-off between delivery fees, item price, and minimum order quantities (MOQ), they often pay more than just necessary. This brings us to the core problem. Why can't just we calculate the cheapest option manually? First, there is combinational complexity. If a bakery needs n item from m supplier, the combination grow exponentially n. Even a small scenario, 10 item, 4 supplier result in over 1 million combination. Second is manual efficiency. A baker might use a simple strategy like always buy the cheapest unit price, but if that cheapest item come from a supplier with high delivery fee and you only buy that one item, you actually lose money. Current method fails to capture these hidden costs. This current manual method also ignores minimum order quantities (MOQ), leading to suboptimal spending. To solve this, my research focused on three main objectives. First, formulate. I will formulate the procurement problem as an integer linear programming (ILP) model using the ISHOPU framework. Second, develop. I will implement a functional computational prototype, Python or Excel solver using simulated market data. Third, evaluate. I will quantify cost saving by comparing the optimized solution against baseline manual strategies. Regarding the scope, I am focusing on a single procurement decision for a small-scale cake lapis bakery. The data used is realistic simulated dataset Kuching market price 2025 and 2026. Exclusion, perishability, inventory, holding costs, and long-term supplier relationship. The significance of this project is threefold. First, academic apply the advanced ISHOPU model to a localized SME context, bridging the gap. Second, practical, provide a data-driven tool for cost saving and operational efficiency. Third, technological, demonstrate accessibility optimization for non-technical business owner. Proceed on chapter 2, literature review. Now, let's look at how this problem has evolved in the literature. It started in 2010 with Beswick et al., who introduced the ISOP, Internet Shopping Optimization Problem. This was the basic model, minimizing price and delivery for single unit. In 2016, Lopez Locus compared exact method against heuristic, highlighting the difficulty of delivery costs. A major breakthrough happened in 2022. Ornelas et al., who introduced ISHOPU. The U stand for units. This adds the reality that we buy multiple units, for example, 50 kg of flour. not just one, and we have minimum order quantities. My research in 2025 built on this by talking that SHOPU structure and applying an exact ILP solver specifically for the scale of local SME. My theoretical framework is based on operation research (OR). We are moved from descriptive analytic, looking at what happened, to prescriptive analytic, which tell us what should we do. Specifically, I am using integer linear programming (ILP). Unlike standard linear programming, which allow decimal, ILP deals with discrete decision. We use binary variable 0 or 1 to decide do we select this supplier, yes or no. We use integer variable to decide how many bags of flour, 10 or 11. We cannot buy 10.5 bag. To clarify where my project fit, please look at this table. Standard ISOP handles single units. The ISHOPU handled in 2022 handle massive global supply chain and use heuristic like genetic algorithm because the problem was too big to solve perfectly. My FYP focused on the localized SME because the dataset is smaller, local bakery scale. I don't need to use approximate heuristic. I can use an exact method, ILP. This means the answer my model give isn't just good enough, it is the mathematically guaranteed global minimum cost. Moving on chapter 3 methodology. My framework follow four distinct steps. First, problem definition. Identify ingredient and supplier. Second, data simulation. Generate cost, metric, and constraint. Third, formulation. Make model, objective and constraint. Four, implementation. Solver, execution, branch and bounds, algorithm. For the simulation, I create a scenario for a typical cake lapis bakery. I construct a matrix of 5 supplier and 5 ingredients. The ingredients selected are the essential for cake lapis Sarawak. First is premium butter, golden drum. Second is Hong Kong flour. Third is grade A egg. Fourth is castor sugar. Fifth is ovalin. This table shows the simulated cost environment. I ensure the price reflect the reality of Kuching market. For example, you can see Back with Yen, specialist retail, offer moderate price and delivery. Honyan, a wholesaler, offer cheaper unit price, 13 and 20 cent for butter versus 13.50 ringgit, but they likely have high delivery fees on strict M or Q. Shopee online might be cheaper for some items but has variable delivery. The model needs to navigate this difference. Now let's get into the mathematics. The model requires several set and parameter. M is our set of supplier, N is our set of ingredient, and our parameter Pij is unit price of ingredient, J from supplier I, Di which is fixed delivery cost for supplier I, Rj required demand for ingredient J, and parameter Aij is available stock and supplier J. We have two key decision variables. Quantity variable integer. It represents the exact quantity of ingredient J purchased from supplier I. Second, activation variable binary. 1. If supplier I is selected, delivery fee applied. 0 otherwise. It means it is 1 if we use supplier I and 0 if we don't. This efficiently turns the delivery fee on or off. The goal of the model is to minimize Z. Total procurement cost. If you look at the formula, the first part is total purchase price for all ingredient, price time quantity. Second part is total delivery fees for selected supplier, delivery cost time activation variable. The solver minimize the sum of these two parts simultaneously. To make the model realistic, we apply constraint. For hard constraint, first demand satisfaction, total quantities purchased equal required demand. We must buy exactly what the receipt require, no less. Second is inventory limit, cannot buy more than the supplier stock. Third is linking, big M. If we buy any item, we must pay the delivery fee. If we buy any item x more than 0, the binary variable y must become 1. This forces us to pay the delivery fee. If we don't pay the delivery fee, y equals to 0 and we cannot buy anything. X must be 0. For soft constraint, supplier preference, implicitly handled by minimizing delivery cost. Fewer supplier equals to lower cost. Second, MOQ, treat as hard constraint in this preliminary model to ensure strict compliance with wholesaler terms. For the technical implementation, I am using branch and bound algorithm. This is an intelligent search method. Instead of checking every single one of the million combination, the solver prunes branch of the decision tree that are obviously too expensive. This allows us to find the optimal solution efficiently on a standard computer. I conduct a proof of concept test to verify the logic. I set up the scenario with 50 units of butter. Supplier A had a cheap butter but high delivery. Total 515. Supplier B had expensive butter but lower delivery. Total is 530 ringgit. The solver correctly selected supplier A. It successfully recognized that paying a higher delivery fee was worth it to get a lower unit price for a bulk order. This confirmed the mathematically logic is sound. This slide presents the project timeline managed via a Gantt chart covering a complete phase of FIP1. For the current semester, our focus was on the theoretical foundation, as indicated by the complete bars. We successfully finalized the problem statement and literature review. Crucially, the mathematically formulation, including the decision, variable, and big M constraint, is complete. Data collection for the baking ingredient case study is also finalized. We are currently strictly adhering to the timeline and are fully prepared to begin the simulation and coding phase in FIP2. By the end of this final year project, I expect to deliver a comprehensive mathematical model tailored for cake lapis bakeries, a working decision support tool, Excel or Python for business owner, quantify saving, evidence of cost reduction compared to manual purchasing. Looking ahead to FIP2, my work will focus on simulation, coding the model into a solver such as CPLEX or Python PULP, and running it with the full dataset. Comparison: if the dataset becomes too large for the exact solver, it will implement a heuristic method like a genetic algorithm to compare performance. Sensibility analysis: I will analyze how sensitive the total cost is to change in delivery fees. In conclusion, for FIP1, the ILP model successfully captured the complexity of multi-unit ordering, which was the missing gap in the literature. The big M formulation has been correctly defined to link purchasing decision with delivery fees. The data is ready for the execution phase.